Good morning, everybody. Today we're gonna review real quick what we did last time. We ended up with section 3 last time, I believe, and that deals with logarithms. Before that, we looked at exponential functions. Those were functions that had x as the exponent and had any number as a base, where a has to be greater than 0 and it has to be, it cannot equal 1. It has to be greater than 0. Because a can be, if your value a is between 0 and 1, the graph looks like this, a decreasing function. If a is greater than 1, then it's an increasing function. That's what we did last time. And we also learned we're going to expand on that today, that exponential functions, and what we're talking about today, logarithmic functions, they're inverses. They're inverses of each other. All right, so again, we looked at, this is example 1. Let's graph that function. Again, if we don't remember what the graph looks like, let's try -3, -2, -1, 0, 1, 2, 3. You remember, so when x is -2, we have 2 to the power -3. A negative exponent simply means change the location. Since this is 2 to the power -3 over 1, we put it to the bottom. So 2 to the power of 3 is 8. So this number here is 1/8. Two to the power -2 is 1 over 2 squared. So it's 1/4. Two to the power -1 is 1 over 2 to the first, which is 1 over 2. Anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 2 times 2 is 4. And 2 to the third power is 8. So the graph looks like this. Now, convert an exponential function to logarithmic. Basically, we're finding here find the inverse of y equals a to the x. All right, so remember, a logarithmic equation looks like this. But remember, it's an inverse of the exponentials. So again, this is the base. This is the base. So they have to stay the same. Remember to find so the bases have to stay the same. Now, to find the inverse, remember we had to switch x and y. So there's the conversion. All right. Let's look for an example here. So let's look at the example. Example 2. This is read log base 10 of 10,000. That's how it's read. Log base 10 of 10,000 is whatever it equals. So to find this value, we'll go back to the conversion. Log base a of x equals y. What happens here is the a comes and pushes the y up. And it stays the base. The base is gone, so the log drops off, equals x. So since we don't know what this equals, so we have 10 to the power y, the base drops off, equals 10,000. Now there's a property that says there are two properties. If the values are equal and the exponents are equal, then the bases have to be the same. Let me switch this over. There's also another property that says if the bases are the same and they're equal, then it means the exponents have to be the same. So what we have to do is try to get the same bases. 10,000 is 10 to the power of 4 because it has 4 zeros. So since the bases are the same, we know that this answer equals 4. So that's A. Question B says log base 10 equals some number y. The base pushes that up, so it's 10 to the power y equals the answer. Anytime we move a decimal, it's always a factor of 10. Since it's moving from the left, it moves from the decimal should be here, it moves 2 spaces to the left, so it's -2. Since the bases are the same, y equals -2. So that's the answer of our question here. Log base 2 of 8 equals some number. So we have 2 to the power y equals 8. 8 is 2 times 2 times 2. So 8 is 2 to the third. Since the bases are the same, y equals 3. So this answer, this equation, log base 2 equals 3. Now what this means is when you read this, it says, what power should the base be raised to equal the number? And I'll call that the number. And this is the base. So what power should 2 be raised to equal 8? Should be raised to the third power. So that's really what it means to with logarithmic equations. D. Log base 9 of 3. Nine comes here. 9 to the power y equals 3, which is what this says. Okay, so 9 to what power? So how do we get from 9 to 3? We know that square root of 9 is 3. And since this is a square root, that means it's a 1/2 power. Whatever the root is, always goes on the bottom. And the real formula for this is whatever the root is, so whatever power still goes on top, and this one goes on the bottom. So this is the true conversion from radicals to exponentials. So since we know that square root of 9 equals 3, square root is the power 1/2. So this is 3 squared to the power 1/2. And so yeah, equals 3. So y is equal to 1/2. E. Log base 6 of 1. This is another property. There are 2 special rules here with logarithms. Log base a of a is always equal. If these are the same, power is 1. Log base a of 1 is always 0. And we'll look at that, why that is. So 6 pushes up the power y equals 1. Now, anything to the power 0 is 1. So y is equal to 0, which is what this rule says. And the last one, log base 8 of 8. So the 8 pushes up the y, and it equals that 8. So this is 8 to the first power. Since the bases are the same, the solution is 1, which is what we said earlier. Log base a of a, if these are the same, then it equals 1. Now let's practice converting between logarithmic and exponentials. Example 3. Given 16 equals 2 to the x, write it as a log. Remember, the log conversion formula is this. So that is your x, this is your y, and that's your base. So it's log base 2 of 16 equals x. That's the conversion. The base stays the base, and the answer becomes the part of the question. Ten to the power negative 3 is equal to 0.001. Convert it into log. The base is 10. This is your answer. And it equals the exponent. And you always check it. To convert it back to exponential, 10 to the power negative 3 equals that. So it's a little bit more difficult going backwards. E to the t equals 70. So we have log base e of 70 equals t, because remember this comes over here. So that's the conversion between exponentials and logarithmic. Actually, we had 3 different types of bases here. Depending on the base, we have 3 types of logs. So instead of typing logarithmic, we simply type log. Here are the 3 different types. If the base is 10, if the base is e, if the base is anything else. Log base 10 of x equals y. If it's base 10, we call this a common log. It's called a common log because our counting system, our numeric system, is already a base 10. We go from 0 to 9, 10 to 19, 20 to 29. 10 numbers inside each of these. We have 10 fingers, so we won't count. So we have, whenever it's base 10, it's common log. So instead of writing base 10, we simply write log of x. In other words, if there's nothing there, if no base, then it is a common log, and it's automatically a base 10. The next one, if the base is e, we call that a natural log. Reason it's called natural log is because that's what happened. This is the equation we use mostly in biology and the sciences, and it's what happens naturally in nature, in the universe. It helps us explain actions and reactions. So if you have a log base e of x, if it's log base e, we simply write ln, the natural log, ln. So if you have an ln, then the base is e. And the last one, any other base, as long as a does not equal 10 or e, you have to write it down there. The reason I said it here was because you noticed in these equations, we have base 10, base e, base 6, or base 2. So this one would be written that way. This one would actually be written like this. There's no base because it's base 10. And this one would be written as LNT. It's just the way that it's written to help distinguish between the three. So let's now do some more conversions. Example 4. A. Log of 645,778. Nope, wrong one. That's example 5. But we're going to convert this one. Convert that to exponential. Again, in exponential, we have the base 2. This is our x and this is our y. Remember, logarithmic and exponentials are inverses of each other. So once we have the base, to find the inverse, you switch x and y. So it becomes 2 to the 5th is equal to 32. Log a of q equals 8. Convert that to exponential. The base is a. This is x and this is y. So when I do the inverse of it, this becomes the y and this becomes the x. So we have a to the power 8 equals q. X equals log base t of m. Write that as an exponential. The base is t. This is x and this is y. Again, it's the inverse. So that's log base t of x equals y. I switch x and y. So my answer is t of x is equal to m. So that's the conversion part. Finding the values. So this is example, let's see, with a calculator. This is example 5. Again, what I don't know why they put this in here. If you have a calculator, you have everything here. So the first one says find the log. 6, and this one I want, and take the log of that, and there you have it. So this answer is 5.81008. So what does this mean? Is since it's the equation itself was log base 10 of 645,000, what this means, this number is if I take 10, raise it to the power 5.81008, I get this number. That's what it means. So let's do the next one. Where's my clear? Well, let's just plug it in there. Yeah. I'll put times 0. Good. So I got cleared it out. 0.0000239, and log of that is a negative 4.61, no, 6.216. Notice it's negative. Why is it negative? Bless you. Because the decimal is to the left of the number. So it means it's very small. It's a negative. So log base 10 of -3. This will be interesting. So let me multiply it by 0. Now I take -3 and take the log of it. Invalid input. Why do we have an invalid input? Because remember, they were inverses. The graph of e to the x looks like this. And since we have to rotate it about the line y equals x, this graph is the log of x, because it's a flip across the y equals x line. Why is it this? because you switch x and y and you get these are inverses. So this is y equals, this is y inverse equals. You notice that the domain of the logarithmic equation is the domain is greater than 0. It cannot equal 0 because it never crosses the y-axis. So you cannot take a log of a negative number. Likewise here. Here, the domain is from negative infinity to positive infinity, but the range is always above 0. It never crosses the x-axis. So the domain of a logarithm is x is greater than 0. The range is all real numbers. So I can have negative answers, I can have positive answers. All right, example 6. Let me put the 3 questions down, or this one has 5. ln of 6, 4, 5, 7, 7, 8. B is ln of 0 0.000239. ln of negative 5. ln of e. And ln of 1. Three of these we can do automatically right now without doing any work with what we've talked about so far. What's this one going to be? Yeah, this one does not exist because x cannot be negative in a logarithm. Remember, ln, how is ln x written? What is its base? E, right? So it's a logarithmic equation. So that means our x's have to be greater than 0. X cannot be negative, so this doesn't exist. How about these? What's this one going to be? You don't see it just yet. ln is log base e of e. What does that equal? Log base e of 1. We talked about these about 5 minutes ago. If the base and the number are the same, what does it equal? 1. And if the base, no matter what the base is, of 1 equals what? Look at your notes. What does this equal? No, this one equals 1. They're not the same thing. You didn't write it down, did you? Again, you should do more than just sitting there stare at the board, because that's the reason I write these things up there. So you could write these things down so we start doing these problems. There wasn't much to write down. I wrote it here. That's all I wrote. Log base a of a equals 1. Log base a of 1 equals 0. That's a general rule. So 3 of them we could do without doing any work. The last 2 are going to be numbers, so we go to our calculator. So let's do the first one. So we have 6, 4, 5, 7, 7, 8, and we take the ln, which is right here. 13.378. If we only wanted 2 decimal places, what would we do? What's the rule for rounding? Yes, since we rounded to 2 decimal, look at the third. If it's between 0 and 4, just drop them. If it's between 5 and 9, add 1. So, oops. So it's 13.378. I want only rounded 2 decimal places. If the third decimal is between 0 and 4, I just drop it. But if it's between 5 and 9, I add 1 to that one. So the answer is 13.38. So that's if I only rounded 2 decimal places. Okay, so let's look at the next one. Times 0 equals 0. So I have 0.000023239. I take the ln of it. It's negative 10.64163. Okay, I want to round it. No, two decimal places. So what's it going to be? If I round it 2 decimal places, so if I'm rounding it, then I go to the third number. I go to the third digit. I look at that one. It's between 0 and 4, so I just drop all those. So that's my answer. So this is using ln and log. These last 2 examples, we're using ln and log. If you notice on a calculator, that's all you have a chance to do. So if I gave you this equation, you couldn't do it on a calculator because all it has is ln and log. Only have log x and ln x. So to find this, any other value, we need to use the change of base formula. In other words, what we have to do here is we have to rewrite this equation into using either one of these. And they're both going to be the same. It's a fraction that we have to convert it. So let's say we wanted to log. So whatever the top number goes on top, whatever the base is goes on the bottom. And same thing for ln. If we wanted to use ln, I could use those. So whatever the operation is goes on top, whatever the base is goes on the bottom. And because it's the ratio we're looking at. So now we can use the calculator. We could do ln 5 divided by ln 3, and that's our answer. Or log base 5. That's the change of base formula. Let me write that. So the change of base formula looks like this. Log base a of x or that's our formula. Example 7 and 8 are going to be using log, using ln. So what would this one look like? If I'm using log on example 7, what goes on top? 8? Just 8? Yeah, look here. Log base 8 over log 5. And this one, since I'm using ln, it'll be ln 8 over ln 5. And that's all there is to it. Graphs of logs and ln. The only difference between the two graphs is how fast they grow. All of them cross at 1. And they all look like that. So here I want y equals log base A. No, no, no. I need a base. Where's my base? Even this one's going to be that way. Okay, so then I'll just do the conversion then. As to trig functions. Yes, remember I said beginning of the semester why I don't like PEMDAS? These are all functions. PEMDAS doesn't talk about any of those. So no, that doesn't work. So let me just do the change of base then. So we'll have division. So on top will be log of x and log of a. Well, let's do log of 2 then. Can't do that. This is going to give me, it's going to give me just a regular function. Well, I can't use that then. Stupid calculator. But pretty much this is what it's going to look like. It's depending on the base. This is log of x. This is log of a, and this is log of a. This is if a is less than 0, or between 0 and 1, I should say. And this is if a is bigger than 1. They're bigger than 10 because it grows much faster. So again, it looks the same, crosses through 1 because that's at 0, it's always 1. So example 11. Remember the transformation chapter? What kind of shift is this one going to be? Because the original graph looks like this. What is this one going to do? It moves, it's a horizontal shift. Set that equal to 0 to -3. So the origin moves back 3 spaces. It still crosses 1 to the right of it. So that's what happened. Your graph just moves back 3 spaces. Remember, review chapter 2. When you do a horizontal or vertical shift, what's changing is the origin. F of x equals 3 minus 1/2 ln x. So let's do this one in pieces. The original graph is ln x. Looks like that. the coefficient in front makes x half as far. Because if at, let's say, some number x, if it was 1, now at the same value, it's at 1/2. So it's a vertical shrink. It's negative. What does the negative do to the graph? If it's outside the function, what does it do? Remember, this equals y, because there's x, so it equals y. So I change the values from x, from positive x to negative x. So the graph looks like this now. Because I switch it, I flip it across the x-axis. That's what that negative does. Now, since this is positive and it's not affected by x, this is a vertical shift. Since it's positive, I go up 3 spaces. Remember, the graph used to look like this. Now I have to go up 3 spaces. 1, 2, 3. So this origin shifts up to here. So there's my new origin. The graph still crosses at 1. So there's your graph. My new intercept, instead of being at 1, 0, it's now at 1, 3. I just shift the whole graph up 3 spaces. And there's an application problem. It's just applying this stuff. And then also in the back of the packets I gave y'all last time, you have this practice. We'll go over these another day. Okay, that does it for that section.